you're going to make a decision about what's the best way to approach this. So, example 4 here. A student is giving a reading list of 10 books from which he must select 2 for an outside reading requirement. In how many ways can he make his selections? In this one here, now first of all, we're going to assume he can't choose the same book twice because, I think most people would be on to him on that one. He has to pick 2 out of a list of 10, so he can't say, I'm going to pick this one and I like it so much I'm going to pick it again. You have to do the outside reading assignment. You need 2 separate books. We're going to assume that. So we could just do it. We say, okay, well, there's 10 books, n is 10, r equals 2, and we're assuming no repeats. Now, the other thing we have to consider here, does the order matter? So if he reads like The Last of the Mohicans and, War and Peace, those are 2 big books. Does it matter if he reads War and Peace first and Last of the Mohicans second? Or does he read Last of the Mohicans first and War and Peace second? No, in the end, he's reading the same 2 books, so it really doesn't matter. So we know that the selection order doesn't really matter for this. So this stands to be a reason for combination. So I can set it up just like this and say, okay, if I do 10 factorial over 2 factorial times 8 factorial, I would get 45 different 2-book selections. Now, a lot of people have a tendency sometimes to confuse this situation and say, well, then I shouldn't I be able to do 10 books, then 9 books after that, and get like 10 times 9 and 90? That seems to be like it seems a logical reason to it, but when you're doing that, you're assuming that you're picking them in a particular order. In this case, you're not. You're not picking them in a particular order. So, if you're doing 10 times 9 and saying 90, that's because you're also saying, okay, if I reverse the order, it matters somehow, and it really doesn't. So that's why there's only 45 different 2-book selections you could have here, because the other way would count some of those more than once. And the last example, a space shuttle crew consists of a shuttle commander, a pilot, 3 engineers, a scientist, and a civilian. The shuttle commander and pilot are to be chosen from 8 candidates, the 3 engineers from 12 candidates, the scientist from 5 candidates, and the civilian from 2 candidates. So basically, there's 8 people. Usually because the commander and the pilot have to know how to fly the shuttle, so they're all going to be pilots, and those are 8 candidates. One will be called the commander, one will be a pilot. So there's going to be 2 picked from that group. From the rest, you're going to pick 3 engineers from the engineer group. You're going to pick 1 from the scientist group of 5, and you're going to pick 1 from the civilian group of 2. So how many different space shuttle crews can be formed based off of this information? So here we actually have a combination of several things. For the commander and pilot, choosing from 8 candidates, I am doing a permutation, because if I select, Colonel Smith and Colonel Jones, and I say one's the commander, one's the pilot, well, it's going to matter which I assign to which. So the order does matter. There is a certain order to the selection. For the 3 engineers, well, I just have 3 engineers. We're not saying it's a lead engineer and other things, payload engineer. I mean, sometimes they do designate like that, but we're just saying 3 engineers. So, if I select, the 3 engineers, it doesn't matter which order I select them. No, if it's the same 3 people, it doesn't matter which order I name them. As far as the scientists and the civilians go, basically all I'm going to do is consider how many candidates there are. And that's going to be the possibilities for them. So when I look for the number of crews, I'm going to do a permutation with n being 8 and r being 2 for the commander-pilot candidates. I'm going to multiply to that the engineer candidates, which is going to be a combination where n is 12 and r is 3. And then I'm going to choose a scientist. Well, there's 5 candidates for that, so I'm just looking for the number of science alternatives there are. And same thing with the number of civilians. There's only 1 out of those 2 being chosen. So when I work this out, this is going to be 8 times 7. So there's 56 there. And I got that 8 times 7 because if I do the permutation and have 8 factorial over basically 6 factorial, that's going to take away all the numbers from 8 factorial except the 8 times 7. They're going to all cancel out. When I look at the combination of 12 and 3, I'm going to have 12 factorial over 3 factorial times 9 factorial. I'm going to multiply that to 5 because it's the number of scientists I have to choose from, and times 2 because that's the number of civilians I have to choose from. So when I put all this together, I get 56 times 220 times 5 times 2, which gives me 123,200 possible crews that could be for this space shuttle mission. And that's just the combinations from these people. So, just from this pure standpoint, now there's other things they would normally look to choose from candidates and things like that and put them through tests and things like that to make them qualify and all that stuff. And the reason why they do all that is because there are so many different possibilities, and that's why if you're chosen to be an astronaut on a mission, whether you're a civilian or a scientist or whatever, it's a very rare thing. So